Welcome to this video on lesson 8 in the forces of space scheme of work. This is on balanced forces, and as you can probably infer from the title of this lesson, the main gist of this is about Newton's first law, and this idea that when the forces are balanced, there is no change in motion. In this lesson, actually, we're just looking at stationary objects. In many ways, it's really just an opportunity for students to practice drawing force diagrams and identifying forces. It is also, and I've sort of only realised this on reflection, it's a way of sneaking in Newton's third law through the back door, you might say, without really telling students about it, because we do introduce the idea of the reaction force here. But I don't like to get too far into Newton's third law. I think for those of you who've looked at lots and lots of physics problems, the kind of problems that really require an in-depth understanding of Newton's third law are things like a car pulling a trailer and kind of thinking about the forces in the tow bar and so on. We're not going to get into that at Key Stage 3, that can wait until later. Really, this is just about students being able to visualize when the object is stationary, you've got balanced forces, and so it's worth keeping it quite simple at this stage. So what I've done in these lessons is just in this lesson, is given it a fairly simple I do, we do, you do structure. So the first example is a person sitting on a chair. So what I would do when explaining this to students, I would obviously start by drawing my chair. Something like this can be a fairly simple diagram, and then I draw my person. I'll just draw a stick person like this. Hopefully it's not too confusing that this person seems to be floating in space. Let's just put the arms down like that. So here is a person. Again, this is just a really simplified version of what's going on. Now, again, what we would do here is draw the forces acting in the middle. It might not be perfectly in the middle of the way I draw it. I'm just going to draw it somewhere here, somewhere around the person's bum, okay? And again, you can emphasize students, it just needs to be roughly somewhere in the middle. It doesn't need to be exactly there. So what I'm going to do is show the forces that are acting. Now there's a few things that I want to introduce here. So the first thing, I'm going to draw this force acting downwards like this. This is just prior knowledge, so I could ask students to kind of retrieve this and say, sorry, let me just get that straight. And say, okay, what's that force that's acting? What's the downwards force? They might tell you gravity. You can make sure they're using that language of weight by this point. So this is the weight, like that, acting downwards. And then this is where you introduce Newton's third law. You say, well, hang on. This seems to be the only force acting. So why is it that the person doesn't just fall through the chair? Why, if I, the teacher, am standing here, why don't I just fall through the floor? What's going on there? And what you want to do is elicit this idea that actually there must be something pushing back up. Now this is Newton's third law, that if we push down on the chair, or if we push down on the floor, or the chair or the floor pushes back against us. And we don't need to go into loads of detail about that here. I would just say what that means is there must be a force, an equal and opposite force, which we call the reaction, acting backwards. And it doesn't need to be exact, but I'm going to try and keep these approximately the same length, so just under 3 centimeters like that. And I'm going to tell students that if my force arrows, and we saw this in the previous lesson on Galileo's experiment, that the length of the force arrows somehow represents the size of the force. We don't need to be too exact unless we're doing scale drawings, but in this case I'm going to try and make sure they're roughly the same length, okay? And I'm going to say that this force is called the reaction force, this force that's acting upwards. Now, the final thing I'm going to do here is just put some imaginary numbers on here. So I'm going to say, well, let's imagine this person is about 60 kilograms. So they have a weight of about 600 newtons, okay? And you can ask students then, if the person was not moving, if they were totally stationary, what would the size of the reaction force be? And again, this is kind of assuming that they know Newton's first law. I think they'll be pretty comfortable working out that if the object isn't moving, well, the size of these two forces must be the same, 600. Now, where we can add just a little layer of complexity here is to just think about this in terms of as vectors, really. And again, we're not going to introduce that language right now. But one piece of formalism, which I think is really, really helpful, especially when they get to GCSE and A-level, is the idea of taking one direction as positive. So it doesn't really matter which direction you take. I'm going to take downwards as positive. So let's say all numbers in that direction are positive. And this becomes really useful when we get to the next lesson on unbalanced forces. But then we could say, well, the overall force, and again, I'm going to introduce resultant force next time, but I just want to illustrate this to students. If downwards forces are positive and my weight is 600, well, that's going to be plus 600 newtons. And if that reaction force is going in the opposite direction, so what I've defined as positive, then that is going to be minus 600 newtons. And what that means is that the overall force here, and I can just call it overall force, or if you want to introduce this language, you can even introduce it now. Resultant force or overall force is just plus 600 newtons minus, because I've got plus in the positive direction and then that one's in the negative direction, minus 600 newtons, and therefore I have a resultant force of 0 newtons. Now, this part is going a bit beyond what's even really necessary for this lesson, I think. But certainly those of you who are teaching high priority attaining groups, I think it's good to introduce this because that's going to help them next time. So that would be the I do, and I would go through all of that in detail. I would kind of talk them through this idea of the reaction force, again, glossing Newton's third law a little bit. The next one I did was a car. And I might get them to do this on whiteboards, so you could show them how to draw a car. I just draw very simple cars like this, kind of two trapeziums, one on top of the other, in effect. So there's my car. Again, what I'm looking for on the whiteboards is that they draw the dot somewhere in the center of the car, that they draw a force acting downwards like this. We should draw the road on here as well, because that's kind of important, isn't it? So let's draw the road on this one, because there's got to be something pushing back up. So I would draw something like this. And again, you might ask them to do this on whiteboards, but then you know, if some are struggling, you might start them off with something like this and say, okay, I've got the weight, and I'm going to tell you that weight equals how heavy would a car be? Let's say 500 kilograms, so that might be about 5,000 newtons. Like that, and ask that you could ask them if they'd struggle with the first bit to then draw, well, are there any other forces acting? And they should be able to identify, well, this thing's not moving, so the forces must be balanced. Let's keep that similar again, so that's about 2.5 centimeters, something like that. They should be able to identify that there must be another force acting in the opposite direction, in this case the reaction force. Again, that would also be 5,000 newtons. Now, those of you who have introduced this formalism, you might say, if that way is positive, well then we've got the resultant force here. Is just plus 5,000. That one's minus, so we've got plus, because that's in the same direction as this, plus 5,000, minus 5,000. Oh, and what a surprise, it's 0 again. Okay, it's obviously hidden, but there you can see it there. So that would be the we do, and again, whether you get to this point depends on the class that you've got. If they can just draw a diagram and name the forces, I think that's a pretty good result for a group being introduced to this for the first time. And then what you'll see later in the lesson is there are, I think, 7 more examples. A word of warning, the last 2 examples are the kind of thing you might see at A-level. And again, I don't think it's beyond students in year 8 to think about the force in that way. Really what you want is for all students to be able to understand what's going on with the first 5. Yeah, for those of you with high priority attaining groups, by all means get them to have a look at 6 and 7, but that's not essential. It's just to get them thinking about these concepts in even more depth. Next lesson, we'll look at unbalanced forces.